Welcome to week 6 of iTech 770, Health IT Databases. This week marks a significant shift in our SQL journey. Up until now, we've been working with individual rows of data, inserting, updating, deleting, and joining them. Starting this week, we're going to learn how to summarize and analyze data across many rows at once. This is where SQL becomes truly powerful, especially for healthcare analytics. Part A, what we're doing now, covers aggregate functions, which includes group by and having clauses. These are foundational tools that we'll use constantly in any healthcare database role. Let me walk you through the full scope of this week, of week 6. We have 4 parts. In part A, which is what we're doing right now, focuses on aggregate functions and how to group and filter summarized data. Part B will introduce subqueries, which are queries nested inside other queries. Then part C covers indexing and query optimization, which is about making your queries run faster. And then finally, part D ties everything together with practical use case studies in population health. And these will show you how SQL skills are applied in real-world healthcare quality reporting. Well, let's look back at week 5. Let's recap what we did. In part 5A, we learned about data manipulation language, DML, operations, such as insert to add data, update to modify existing data, and then delete to remove data like rows or records. In the second portion of week 5, we covered join operations, learning how to combine data from multiple tables using the inner, left, right, full, cross, and self joins, all different varieties and flavors of joins. And in the third of the 4 components of last week, part 5C, we explored interoperability and electronic health record EHR vendors such as Epic and Oracle and Meditech. And we also discussed TEFCA, TEFCA. And then finally, part 5D was our deep dive into the USCDI, the United States Core Data for Interoperability. So the key transition to understand here is, last week we were working at the row level, manipulating individual records, and this week we moved to the set level analysis. Instead of asking what is this patient's blood pressure, we're going to ask what is the average blood pressure across all our diabetic patients. That shift from individual records to population level summaries is what aggregate functions enable you to do. By the end of today, part 6A, you should be able to accomplish 6 things. First, understand the purpose and the syntax of the SQL aggregate functions and when to use them. Second, to learn how to use each of the 5 core data aggregation functions, which include count, sum, average, min, and max, and actually how to apply them to our xHealth healthcare data set. And third, to use group by to break results into meaningful categories or subcategories, such as by insurance type or provider. Fourth, learn how to filter those grouped results using the having clause. And fifth, clearly distinguish between where and having. This is a common source of confusion for students. The where and having have some similarities, and using them incorrectly will mess up your output. And sixth, the final for this lecture, is to combine the aggregate functions with joins to perform multi-table analysis, which is where things get really powerful for healthcare analytics. But with the power comes complexity. These are sophisticated data analysis tools. And this is the crux of medical databases. This section introduces the concept of aggregate functions. Think of this as the moment where SQL stops being just a data retrieval tool and starts becoming an analytics tool. Everything we do in healthcare reporting, from quality measures to financial analysis to population health, depends on aggregating patient records from individual data into meaningful summaries. For some of you who are not familiar with coding, this is going to be a stretch, but we will keep the examples concrete and healthcare relevant for you to appreciate the logic. These are foundational skills if you hope to contribute to healthcare data analytics. An aggregate function performs a calculation across a set of rows and returns a single value. This is the core concept. Instead of getting back 10,000 rows of encounter data, an aggregate function can tell you in one number how many encounters there were, or what the average BMI was, or what the highest blood pressure reading was. These functions are essential for reporting and dashboards. Anytime you see a summary statistic in a healthcare dashboard, whether it's total patients served, average wait time, or revenue by department, there's an aggregate function behind it. One critical thing to remember, aggregate functions automatically ignore the null values, with just one exception. Count with the star, count star, counts all the rows regardless of the nulls. We will see the practical implications of this as we go through some examples. The basic syntax is straightforward. Select the aggregate function from a column name in parentheses, from, and then the table name, with an optional where clause to filter before aggregating. So the healthcare context here is important. Questions like how many patients have diabetes, or what is the average blood pressure across our hypertensive population, cannot be answered with basic select statements. They require aggregate functions. Here is your reference table for the 5 different aggregate functions that you need to be aware of, that you need to know how to use. Let me let you walk through each one. Let's take a minute and stand back and look at this list, because you're going to be using this a lot. The 5 aggregate functions are count, which counts the rows or the values, and it works with all data types, not just numbers. The key nuance is that count star includes the nulls in the count, whereas count of a specific column will exclude the nulls. Then, second, sum adds up all the values in a column, so it's only going to work with numeric data. If you try to do a sum on a text column, you're going to get an error. As expected, it ignores nulls. A null is not a 0. The record is ignored in the calculation. Then thirdly, average calculates the arithmetic mean. And again, this only uses numeric data. And here's the important subtlety. It ignores the nulls in both the sum and the count. So if you have 100 rows, but 20 are null, average will divide by 80, not by the 100, not by the number of rows, but by the number of rows that have legitimate data. And then we have count. Let's dive into count, which is probably the most frequently used aggregate function. There are 3 variations you need to understand. Count star counts all the rows in the result set, including rows where some columns might be null. This is your go-to for how many records are there. Count with a column name, if you specify the column name, counts only the rows where that specific column is not null. So if you have 500 patients, but only 450 of them have, for example, an email address, count star is going to give you a 500, but count with specifying the column email will return just the number 450. What is count distinct? Count distinct counts unique non-null values. Think about that. This is extremely useful when you want to know how many different values exist, like how many unique insurance types do we have. Let's look at these examples, these code examples. The first query answers the question, how many patients are in our system? Count star as, and giving it an alias, total patients, if you're going to use the data in a report, from patients. Straightforward, simple code. It's going to give you the number of rows in your table, the number of patients in your database. When you select count of email as and giving it the alias of patients with email from patients, is going to ignore the nulls. And finally, the final example, select count distinct insurance type, then giving it the alias insurance types from patients will give you a count of how many different insurance providers are in your database. These are 3 examples that show count applied to real health scenarios using, for example, our X-Health database. What does the first code do? Select how many encounters occurred in 2025. How would you write that code? Well, you start select count star, because you want to know how many rows, as, and you're giving it the alias, a name for this variable, total encounters. You're getting it from the encounters table, and you're going to specify where encounter date between, and then specify dates in the proper format, January 1st of 2025 and December 31st of 2025. Now remember, when you specify dates or specify a between, it's inclusive. It'll include both the first and the last, both ends. The next example, how many patients have a primary care provider? You select, then you're going to count the column primary care provider ID, so that means it's not null, and then we're giving it the alias as the patients that have a PCP from patients. So that's going to go through all the rows, all the patients, and find the ones that have a not null value for the primary care provider ID. And our third example, how many unique diagnoses have been recorded? So in that case, we do the select count distinct. When you say distinct, it's just going to give you count of how many distinct answers are in the ICD-10 code column. So, and you're going to say as, you're going to give the alias of what the name of this variable is, unique diagnosis. And this is coming from the diagnosis table. So we're finding out how many distinct entries are in our diagnosis table. So this gives you insight into the breadth of the type of conditions that we're managing and the different use of the count capabilities. How about the sum function? This is totaling your values. Sum is a very straightforward capability, and it's essential. It's especially used in financial analyses. It's going to add all the non-null numeric values in a column and return to you the total. Now, 2 important behaviors that you need to understand. Sum only works with numeric data types, and it'll return a null if every value in the set is null. So if you're doing a query that only selects a small number of records and it turns out that all of those have a null value in this column, you're going to get a null. And that's distinct from a 0. So you can't assume that it's going to give you 0 if all the answers, if that's a realistic answer. So keep in mind when working with tables that might have sparse data, that there is a workaround that you can do, but it's kind of complicated, that if you need to test the result to say, add the condition that if is null to return 0, because null is not a calculatable, it's not a answer that you can use in a calculation. So we can see how complicated coding can become. Let's look at our examples here, 2 examples. The first one is we want to total the charges across all the insurance claims. So how are you going to get that information returned to you? You're going to select the sum of all the total charge as, and you give it the alias that we're going to call this result total charges, and it's coming from the table insurance claims. So there's a column in insurance claim is the total charge, and when we do the select, it's going to sum all the charges for all the patients, from all the insurance claims in that table and give you your total charges back. Very straightforward. This is a common type of query. Look at this other example, the total patient. The total patient responsibility for 2025. We want to know how much the patients are responsible for. So where do we have that stored? It's in the insurance claims. So we're going to select the sum. We want to add up all the patient responsibilities. That's the column patient responsibility. And we're going to report this sum as the variable total patient responsibility. It's coming from the insurance claims table, but we only want to select the rows where the claim date is between January 1st of 2025 and December 31st of 2025. So we're going to get all the patient responsibilities for 2025 through these simple 3 lines of code. In healthcare financial analyses, sum is used frequently, especially for revenue cycle management and sometimes for payer mix reporting. What about the average function? We're calculating averages. This is going to return the mean average of a set of numeric values. Remember again, as when it's dealing with numbers, it's going to ignore rows where there's a null value. So the denominator only counts the non-nulls. And a lot of times when you average data, it's going to give you lots of decimal precision, and sometimes you just want 1 or 2 decimal points. So you can specify that by using the round additional function for far cleaner outputs. Now, remember, it ignores the nulls in both the numerator and denominator of the average calculation. So when you see the tip on that slide at the bottom there, it says if you have 100 rows and you have 80 values and 20 nulls, the average is going to divide by 80, not by 100. So this can lead to results that are a little different than you might expect if you're not careful. And second, I recommend always wrapping average in round for a clear output. Like example, the average of the BMI might return something like 28.3472. Round it with 1 decimal place is going to give you 28.3, which is a far more readable output. Now the first example of these two calculates the average BMI across all encounters with a where clause filtering out the nulls explicitly. While average already ignores the nulls, the explicit filter here is a good practice for better clarity. And the second example calculates the average charge per insurance claim, rounded to 2 decimal places for proper currency formatting. 2 really good examples. What about min and max? Min and max are your tools for finding boundary values. They're especially versatile because they work across multiple data types. Like with dates, minimum gives you the earliest date and maximum gives you the most recent date. With numbers, they give you the smallest and the largest values. And with text, min returns the alphabetically first value and max the last. The first example of our 2 examples here finds the oldest and youngest patients by looking at min and max of date of birth. Notice something quite subtle here. The oldest patient has the min date of birth, the earliest date, and the youngest patient has the max, the most recent date. This can be a little bit counterintuitive, so make sure that you think about what min and max means in context, especially like a date. The second example finds the blood pressure range by getting the lowest and highest systolic readings. The where clause filters out nulls because we do not want null values interfering with our range analysis. This kind of query is useful for identifying potential data quality issues too. If your minimum systolic blood pressure is 0 or your maximum is 400, you know you have some problems with your data entry, your data quality. which needs a little further investigation. Now, as a powerful feature of SQL is that you can use multiple aggregate functions in a single select. This lets you build comprehensive statistical summaries in one query. The example here creates a complete encounter statistics summary in a single query. Let's look at this carefully. The total encounter count, the date range from first to last encounter, the average BMI, the systolic blood pressure range, the average heart rate. It's essentially a mini dashboard all in one query. Look at this. Go through it line by line. And another thing to be cognizant of is the aliases. Every column is given an alias so that you can understand what your output variables are. When you use aggregate functions, the result columns have no meaningful name by default. So by using the alias in Postgres, it gives you a name that you can use for later analysis. Always use the as to give your aggregated columns clear, meaningful names. This is especially important when building reports or your query feeds into dashboards or some other type of application. All right, what do we do about filtering before aggregation? The where clause. This slide reinforces a critical concept. The where filters individual rows before the aggregation begins. Only the rows that pass the where condition are included in the aggregate calculation. So the first example calculates the average BMI for female patients only. Notice the join between encounters and patients so that we can access the gender column, which is only in the patients table, not in the encounters table. The where clause filters to female patients, and the not null BMI values before the average is calculated. This means the average is computed only over the female patients' BMI readings. All right, how about the second example here? It counts the chronic diagnoses by filtering the quote is chronic end quote column. So only rows where is chronic is set to true will be counted. So you need to remember, you need to understand this. You filter first, that's your where. Then you aggregate. This behavior is essential because it contrasts with the having clause, which we will cover next shortly. The where aggregates on individual row values. You cannot use an aggregate function in a where clause. If you try something like where counts of stars greater than 5, you're going to get an error. That's what the having clause is for. All right, let's take a look at group by, categorizing data for meaningful analysis. This takes aggregate functions to the next level. Without group by, aggregate functions operate on the entire result set and just return a single row. With a group by, you can calculate aggregates for each category or a group separately. And this is where healthcare analytics really starts to take shape, because we almost always want to see metrics broken down by things like the provider or the insurance type or diagnosis or certain time intervals and so on. So it's very important to be able to do the group by. Group by splits the results into groups based on their values in one or more columns. Then the aggregate function calculates separately for each grouping, producing one row for each group. This is critical. But there is one rule that I want you to commit to memory. Every column in your select clause that is not inside an aggregate function must appear in your group by clause. Postgres strictly enforces this rule and will throw you an error if you violate it. We will see an example of this error in a few slides forward. Here's your syntax. Select, and then the grouping column, and your aggregate function from the name of the table. Optionally filter with the where, if appropriate, and then group by in the column you're categorizing on, and order by to sort the result. So there it is. Let's look at group by with just a single column. This is your first real group by example, the simplest. We're going to count the patients by their insurance type. This query is going to select insurance type and count star, groups by insurance type, and orders by the count in descending order. So what's the output? This is an excellent example. You get a table that shows the insurance type, Medicare, Medicaid, private, self-pay, or uninsured. And the patient count, we have 145 Medicare patients, 130 Medicaid, and see it's already sorted by patient count descending. So this is a great little query, a great little report that uses a lot of the power of your select using your group by and order by capabilities. The expected output table shows what this would look like. This is a fundamental payer mix analysis. In a real community health center, understanding your patient population by insurance type is critical for good financial planning or for allocating resources and to identify potential access barriers for uninsured patients, for example. Now let's look at group by with multiple columns. You can group by 2 or more columns for a deeper breakdown. When you group by multiple columns, each unique combination of values across those columns will become a separate group. Let's look at this example. It groups encounters by both encounter type and year. So you might get groups like annual physical for 2024 or annual physical 2025, sick visits for 2024 or sick visits 2025. Each of those is separate rows, so it lets you see trends over both time and visit types. Notice the use of a special function called extract year from encounter date. What is that going to do? Think about it. Extract year from encounter date is just going to pull out a 2-digit number to give you the year that you can use this as a value in your Postgres query. This is built-in function with Postgres dates. Is very commonly used. And then the group by for time-based analysis. The same expression appears in both the select and the group by, which satisfies the rules we've discussed. All right, let's look at group by in healthcare analytics. This example demonstrates a more complex real-world healthcare query. We're going to calculate the average systolic blood pressure by provider, which is a provider benchmarking query that is used in quality metrics and can influence a physician's reimbursements. Insurance companies are becoming increasingly concerned about the quality among different providers, and so queries like this will help an organization, a clinic, be able to document which providers are getting the best blood pressure control. So let's look at it carefully. This query does a join. It's going to join the encounters with the providers so we can get the provider's name and their credentials. It filters out the null blood pressure readings with the where clause. It groups the provider, the last name, and credential, and for each provider, it calculates their total visit count, and the systolic blood pressures can then be averaged. The note at the bottom is important. This type of query, look at this. This type of query enables provider performance benchmarking, a key component of value-based care. Health systems use queries like this to identify providers whose patient panels have higher or lower blood pressure control rates, which can inform the quality improvement initiatives. Notice that this query combines several things that we've learned. We got the joins from last week, the where filtering, the group by, and the multiple aggregate functions. So go through this slowly and carefully and be sure that you understand every component of every statement. Which columns are we selecting? We gave it an alias. We're counting doing a count that's going to give us the total number of visits. We're going to round the blood pressure and with just one decimal place. And we're getting these from the encounters table. We're joining the providers and giving it the alias P. on the provider ID equals the encounter provider ID equals the provider's provider ID. And we want to know where the blood pressure is not null, because if a null would ruin your statistics. And we're going to group it by the patient's last name, by the provider's last name and the provider's credential. Then we're going to order it by the average systolic, so that each provider will get a line in our output printing out the average systolic blood pressure among their patients. An excellent query. All right, let's look at the group by, a common error that people make. This is one of the most common errors students encounter. So look at this carefully. The rule is simple, but strict. Every column in your select clause that is not wrapped in an aggregate function must appear in your group by clause. The wrong example here is select specialty, last name, and count star, but only groups by specialty. Postgres does not know what to do with the last name because it's not being aggregated and it's not in the group by. You have to think of it this way. If you group by specialty and there are 5 doctors in internal medicine, which last name should Postgres display? It cannot pick one, so it's going to throw you an error. The error message is very descriptive. Column providers.lastname must appear in the group by clause or be used in the aggregate function. So when you see this error, you have 2 choices. You can either add the column to the group by or wrap it in an aggregate function like max of last name or count of last name. The correct version includes both specialty and last name in the group by, creating groups for each unique specialty-name combination. All right, let's look at the having clause, filtering groups after you've aggregated them. The having clause completes our aggregation toolkit. Where filters rows before grouping, having filters groups after they're aggregated, and understanding when to use each is one of a key skill that separates beginner SQL programmers, users, from intermediate and advanced ones. Having was added to SQL specifically because where cannot use aggregate functions. If you want to filter based on a count, or sum, or average, or any aggregate result, you need having. Having always appears after group by in the query. It evaluates the aggregate value for each group and keeps only the groups that satisfy your condition. Here's the syntax. It shows the full structure. Select, and then give the column name, and then the aggregate function, whichever you choose. Then from, and you give it the table name, and the where, so you have a condition to which rows to select, and then group by, which column do you want to group them on, to sort them by, then having, what condition do you want the members you want to analyze, what condition must they meet, and then finally to order by, to sort the output. This has a little bit of everything. This is a very commonly used structure, so look at it carefully, be familiar with it. Okay, let's try to differentiate between the where and the having, because there's a little bit of overlap, and we talked about that earlier, saying this is a common source of errors. This comparison table is one of the most important references in this lecture. And let me walk through each row. The where filters individual rows. The having filters the groups. Group by, having runs after. So where cannot use aggregate functions, but the having can. So where works perfectly fine without group by, but having is rarely used without it. So where answers which rows should I include in my analysis, but having answers which groups meet my criteria. So the analogy is helpful. Where is the bouncer at the door who decides which individual records get into your party. The having is the VIP filter that looks at the groups already inside and decides which groups are important enough to stay in the final result. So the common mistake that I see is trying to use where with an aggregate. For example, where count star is greater than 5, it's going to throw an error. You need to have having count star greater than 5 instead. It just takes some experience. It just takes doing. So having in practice, this example, look at this carefully, finds the providers with more than 200 encounters. We're going to join encounters with providers, and we're going to group by provider name and credential. We have to put them both together so we don't get a violation. And then use having to keep only the groups where the encounter count exceeds 200. So notice that the having clause uses count of e.encounter ID greater than 200. This is an aggregate condition that cannot be expressed with a where. The count has to be calculated first through group by, and then having filters the final results. So in a healthcare context, this query identifies your highest volume providers. This information is useful for workload balancing, or compensation analysis, or identifying providers who may need some additional support staff. Very useful information. All right, what about combining the where, group by, and having? This happens very frequently. So this slide is going to bring all this together and shows the complete SQL execution order, because that's what you need to understand. It's what order are the things actually executed. This is crucial for writing good code. The execution orders we talked about in previous weeks is from identifies the table, where filters the rows, group by creates groups from the remaining rows, having filters those groups, select determines which columns they're going to return, and order by sorts your final results. The example query here demonstrates all of these working together. We're looking at insurance claims, but only for 2025. Where filters the date range first. Then we group by payer name. Then having keeps only the payers whose average charge exceeds $500. And then finally we order by average charge descending. The note at the bottom reinforces this, the little on the slide. The step-by-step flow. Where filters claims to 2025 first, reducing the data set. Then the group by groups the surviving rows by their payer. Then having evaluates each payer group and keeps only those with an average charge above $500. What about conditional aggregation with a case clause? The case statements with aggregate functions, it allows you to create what are essentially a pivot style analysis all within a single query. Look at this example. It breaks down each patient's diagnosis into chronic versus acute by counts. The sum with the case pattern works like this. For each row, the case expression evaluates to 1 if the condition is true and 0 if it's false. The sum then adds up all those 1s and 0s, effectively counting how many rows met the condition. So the sum of case when diagnosis.is chronic is true, then 1 else 0, and is going to count the chronic diagnoses, and the similar expression with false counts the acute diagnoses, all within the same query. This pattern is extremely powerful for healthcare analytics. You will see it used frequently in quality measure calculations, where you need to count how many patients in a denominator meets different numerator criteria. And we will revisit this pattern in part 6D later this week when we discuss the HITIS measures, the quality measures. So the limit 10 at the end restricts the output to the top 10 patients by chronic diagnosis count, which is useful to identify patients who may need chronic disease, additional management interventions. All right, so now I want to encourage you to try this yourself. Try to write a query that will count the number of active patients per insurance type. See if you can do that yourself. It requires a group by on insurance type and a where filter on is active. Look at 2. Find the average BMI by gender. We've already been through this once, but see if you can do it on your own. What do you need to do? You're going to need a join between the encounters and the patients. Why do you need that? To get the patient's name. You have to join those 2 files. Then you need a group by on gender. Very straightforward. Number 3. Providers with more than 50 medications requires a join between the medications and providers with a group by and a having clause. Number 4, what are the top 5 ICD-10 codes? It's going to use a group by on the ICD-10 code with an order by, count descending, and a limit of 5. So just with these simple brief statements, clauses, you can make a very sophisticated query. And the final example, the total charges per payer with a threshold filter, which is going to combine your group by with a having and a sum. So now you're practicing writing your own SQL Postgres code. All of these exercises are using our xHealth Community Health Center database. So try to write these queries in your PG admin before looking at the solutions. See if you can do them yourself. So what have we learned? What are our takeaways for Part 6A? First, the aggregate functions transform row-level data into summary statistics. Count, sum, average, min, and max are your 5 core tools. Second, group by organizes results into categories. Without it, aggregates operate on the entire table, but with it, you get per group calculations. Third, the having filters groups after aggregation, while where filters rows before. Never try to use an aggregate function in a where clause. That's very tough. You have to remember that. Think of that. And fourth, always use column aliases with as when using aggregate functions. Using aliases, very important. It's good coding practice. Your output should be readable and self-documenting. And fifth, null handling varies by the function and can be very important for data accuracy. Like count star is going to include the nulls, but everything else is going to ignore them. So you need to understand this, the implications of this for your specific analysis. And sixth, the SQL execution order is from, where, group by, having, select, order by. Let's go over that again. The execution order is from, that's which table, where, your criteria, group by, having, select, and order by. You have to know this order so that you can write your queries properly. So coming up next in Part 6B on subqueries, where we learn how to nest queries inside other queries for even more powerful data analysis.